Hello, welcome to video 27 in our lecture Advanced Mathematic Modeling. In this video I want to say you some words how you can best analyze random walks. So you might stumble across this either if you have some data that you want to analyze and you can interpret this data as random walk. And I gave you many examples like stock markets, temperature curves, positions of walkers that you can really interpret as such a random walk. Or maybe this is the result in your homework of your realization of a stochastic process and you get such a trajectory. And now you want to know what's the properties of this random walk. So what can we do? And basically we learned how to estimate moments and probability distributions for random variables. And when we have a random walk, we have just to do this for different time points. So essentially it's the same as estimation of characteristics of distributions, only with the complication that we have to do it for all kind of time points. But there is some specialities and I want to discuss this. And so my first recommendation would be very first, make a plot. And this is so important, because sometimes in your computer you can realize these realizations of random walks, and if you have your algorithm which can obtain properties of this, sometimes you may forget to plot the trajectories. But that would be a mistake, because very often, for example, you have a bug in your code or something, and if you don't plot it you will not see it. Or you have something, you look at this and you directly from the eye will see some patterns here. For example, here you would say, oh, maybe there is an increasing trend here. Maybe it's a biased random walk. Maybe x on average is increasing. And our visualization system, our eye, is so good at detecting these patterns. If you have data, make a plot first before you analyze anything. And then you can decide which algorithm you do, because of course you don't want to stop with the idea, oh, maybe it's increasing. You want to quantify this. For example, you want to have the slope, and in the end of the day maybe you want to have a p-value to really see if this is really increasing or not. Maybe also we okay, now we have this. So what can we do more? I mean, the most complete information of course would be if at every time point, and I have not only one realization but I have many of them, and then I can take a time point here, make a line through this, have all the realizations, and then obtain the probability distribution, and maybe it would look like this. And so we would see, oh, we have here p of x and t. That of course would be the most ideal situation, and if we could do this probability distribution for every time point of our walk. So a goal sometimes would be to make or find the probability of the distribution, find p of x and t, and the idea would be to make histograms of x for all kinds of time points. But very often we will not be able to do this, in particular if you have real data, experimental data, because you need many realizations of this. In order to make the histograms you need a lot of data, so very often we will not be able to do this. And then if we cannot get the histogram, maybe we are able to find moments. So we maybe find the mean value, and the mean squared deviation. Yeah, so first and second moment of our walk. And for example, here we would be interested, if we know if we can now for every time point have a mean value, and if it's really like this, that the mean maybe here would increase in time. So maybe the expectation of x would be proportional to a constant times t, yeah? And then we would see, okay, it's a biased walk and we are increasing in time. So how do you find this? So we have at different time points to estimate the expectation value of our distribution and then see, does it increase in time? And then of course we're interested in the standard deviation. So we're interested in the typical deviation of this. So we want to know what is the deviation of x minus the expectation value of x, this squared, the square root of this. Yeah. So this gives us a typical distance of our, actually it's only, no, I did it in two directions. So actually it's only the distance from the blue line to our point of the trajectory. And this of course we can also do for all time points, and this is the mean squared deviation that we are interested in. Now the thing is, all of this what I said before we can do if we not only have one realization but many here. So let's say we have another one which goes like this, a third which goes like this, and another one. And so we have this whole cloud, and then at every point we can average and calculate our normal things. But what do we do if we have only a single realization? What if there is only a single realization? What do we do now? And actually that's a typical case in biological data, for example, or in other situations where you just have one such thing. Okay, so let's say we have now this here. We have time, we have our displacement, or our random variable, and now we have just this one thing. What can we do? And there a trick that you can do is, if the whole thing is very long, if at least you have only one realization, but this realization is very long, so you have a lot of data, so you can assume now we answer this question here. So we assume we have a stationary process. And if the process is stationary, I mean, this would mean that the properties of the process don't change in time, and then I can average over different positions in time. So I mean, when I was doing this here, so we picked a certain t value, and then we were interested at this time, what is the typical distance here? You could also say when we start from 0, we take a certain delta t, where we start from 0, and we want to know what is a certain delta x. Yeah? And I can always start from 0. I have the luxury to start from 0 because I have many realizations. So if I take this time point, I have many results. If I have only a single trajectory, then I have to find different starting points of my trajectory, because only my time series started maybe by accident at this point, because maybe that's the first moment some person measured something. This doesn't mean that I have to regard my time series from this point. I can also say what would happen if I start at this point here. So let's take this point here. Now I go a certain distance delta t to the side. And now I want to know, so I go a certain delta t in the future. And now I'm interested, what is my delta x? This distance that I have, the displacement that my walker has done, starting from this point at a certain time t. And now I take another point, maybe I take this point here. Again, I go the same distance to the side. Oh, here for example I will find that basically it's a cool example. So here, yeah, maybe if I go here, then I see here this delta x would be very small when I have this point and this point. So I started here with these 2 time points, and then I have these 2 time points, and now I can take, for example, this starting point. I go at a certain distance, delta t, and try to find delta x. Then I have these 2 points, and basically I can do this for every starting point in my walk. I can do it for every point where I have at least data at some time distance delta t. Yeah. Now the question is, and then I can make a plot. Now I have a certain delta t that I picked. For every delta t I find a whole bunch of delta x's here. And from all this delta x's here, so I take a certain delta t and I find a certain bunch of delta x's, and I can plot all of these. And then I have here my distribution of the delta x's. So then I take maybe a smaller interval delta t, and I can find a lot of such pairs. I take a smaller value of delta t. I calculate a lot of these values of delta x's and find again maybe here a certain count of point. Then I take a smaller delta t, and calculate my typical delta x's. Then I take a larger delta t and calculate my typical delta x's. And then I try to see if I can make here a line through this. And then for every of these chosen time intervals, I see what was the corresponding displacement in space or in my state variable, and then I will find the mean value. If I have long enough time series, I can find my histogram, and I can find here the mean squared deviation. Yeah? So that's very often the trick that you do. Now the question is, what is this delta x? Yeah? And there again, there's different possibilities. So let's start again with a trajectory t and x, and let's maybe we start here. Maybe we have this, and this was my chosen delta t, and this are my 2 points. And now I want to know, at this time scale of delta t, what is my typical delta x? Now there's different possibilities. So one thing what you could do is you can take the starting value and then you can take the final value and just say, for example, we take here this here as delta x. Or when we want to calculate expectation values, then we can say we take from this distance here, we take, for example, now you can look, for example, the absolute value of this delta x. Or you could be interested in delta x squared, take the expectation and take a square root. Or we could just take the expectation of this absolute value. But you could also say we take the whole interval and I take the mean value of the whole trajectory in this interval. So you take all the data here, you look what is the mean value. That would be maybe something like this. And then it would be here like the mean of x of x of t in this interval t from this delta from this time interval here. So you take the mean value of all this, or you could say maybe I choose the max value. Maybe I say actually this is my delta x. I want to know what is the maximum value that my trajectory obtained in my interval delta t. So we could also say, for example, what is the max of all t in this interval of x of t. And these are different possibilities. These are all functions which depend on your time interval. And now then you make either plot. We choose different values of delta t and calculate whatever is here, this delta x here. So the characteristic displacement, which could be one of these. And now you have to choose some values. You choose different values of delta x, calculate your expectation of this as a function of delta t and make a line through this. But then very often we are interested, is this a power law? If we want to know if this is a power law, then we know how to do it. So then it means our typical displacement delta x should go as our time displacement to some power alpha. So for this we need a log-log plot. We plot log. Very often I take log in to 10, log 10 of delta t, and here also log 10 of our delta x. And again, remember, this delta x is one of these quantities. But now if I want to have good equal sized points, this means I need to take here a lot of measurements for small delta t's and not so many measurements for larger intervals, so that I have, in optimal case, I have equal intervals on a log scale. And now I plot for each of these values my log of delta x, and then I hope that I find here a straight line. Then I can make a straight line fit. We look for the slope, and with this slope we can see if this is estimate if this is a certain alpha, so whether we have here a power law. The problem is sometimes with these power laws it's a bit tricky, and you will see it in the exercise. You could have a slight curvature here, and then it's not so clear actually, do you have maybe power law only in this range, or a power law with a different slope in a different range, or a whole power law over the whole interval which has a mean slope, so that actually it's a bit tricky to calculate slopes of this. And I mean, when you simulate something in the computer, of course we can do more and more data, and then you will see if you get more and more data, the errors get smaller. And then you will more or less see if you have different scaling exponents in different regimes, or if you have a single straight line through the whole data. But what if you have just experimental data where your resolution is not so fine? So for example, what I often do when I have something like this, I plot here the slope of these points as a function of delta t. And if it would be a power law, the slope, so the difference to the next points, should always be the same. But if I see here over the time that if I now calculate the slope in a different color, if the slope would be something like this and then decays a little bit, and then I would see I have a typical transition between two different slopes. But if it's a constant more or less, then I would say I have a power law over the whole data. But this is the strategy very often that we do, because we are interested to characterize our random walk by its mean square displacement. We want to know, if we go a certain step in the future, what is the typical displacement in our state variable. We do it either by looking for all realizations, or we take different starting points in a single trajectory. We need to find a way how to characterize this here absolute value, the max in the trajectory, the standard deviation. Plot it on a double logarithmic scale and try to see if we find some power laws or not. And now the interesting thing is, if we really have a diffusive process, and then this universality holds again, and all these things will leave us the same exponent, alpha equals 1 over 2 for the diffusive class. There it will make not a difference. But if we later go away from the diffusive class, so we go to random walks which are not just diffusive, such subtle differences can suddenly make a lot of problems and will make really a difference in practice. Okay, now let me do one final remark. Is there's all these questions how to analyze something like this and try to see, is there maybe bias in this data, and how is the power law, this random walk characterized? Is this just academic, or can this be of real interest? And indeed, in many cases this can be of real interest. Just let's give you first example. Let's assume that's the stock market, yeah, which is actually fluctuating a lot more than what I have here. And you're interested, does the stock in my country over the last 20 or 40 years or the last 2 years, does it increase in time or not? So you want to know, is this increasing function, is this a random walk with a positive bias or not? And the question is tricky to answer because a lot of time it goes down. And if you would just look at a small time window here, for example, the trajectory has a tendency to go down. But if you look at a larger time window, the trajectory has a tendency to go up again. So if you see a downward or upward trend, is this just because it's a small piece in a fluctuating trajectory, which always sometimes has to go down? Or is this the general trend? And this question has never been stronger formulated or discussed than in the current climate debate. And there it has become famous under the name the hockey stick graph or hockey stick curve in climate research. And so you all know we're wondering if our temperatures on Earth are increasing or not. And there is a lot of people who don't believe it, and most of the scientists are very sure that temperatures are increasing. And so what you do, you try to make a time series. And this has been done by geological reconstructions. And so there some very classic constructions are, if we go in the time back, so here we have time. Maybe here we have the year 2000, and maybe here we have the year 1000. And now you can go in different time windows back in history. And now here we look at the temperature element. So what we mean by this, so we try to find out in centuries, some centuries before us, what was the typical temperature on Earth, and so we look at the deviation from something normal. Yeah? So we have maybe here some 0, so we measure this in degrees, and here we have here something like minus 0.6 Celsius, and here we have plus 0.6 degrees Celsius. And now we have here the something like this. And if the climate would be stable and there would be no warming, then the temperature curve would be a fluctuating number, but would be so basically kind of a random walk, but it would always be centered around 0. So we would have something like this here. And then the problem is, by chance, sometimes you have increasing trends, sometimes you have decreasing trends, and you will have this because the next temperature in your next year or your next measurement point is the old temperature plus the increments, and the increments are given by the climate processes. Yeah? And so the temperature really makes a random walk determined by climate processes. And so this reconstruction has been now done a lot of times. There's a lot of tricks how to do this, and I will not enter this so much. And in fact, what we found, it looks like it goes a bit down here, but since a couple of years we find suddenly something like this. Actually, so it looks like this. And so the first to really scientifically plot such a curve, this was Michael Mann. And he analyzed such a reconstruction of Earth surface temperature. And you can now also look at the uncertainties of this, and the more you go back in time, typically the larger the uncertainty is. And when you look at the uncertainties, we have here certain, and if you go 1,000 years backwards, we have a certain arrow here. And if you go in the, sometimes the arrow even there goes up and down. Now recently the arrow gets smaller, and so we have also a certain here arrow that we don't really know what the climate was. But there seems to be a tendency in the last decades to have a warming. But this was now the big debate: is this really warming, or is this just one of these small scale growing phases that you always will expect in such a random walk? And now you have the debate here. We have only a single trajectory. We have only one history of climate on the planet. Of course, you can get different trajectories, and people did this when you look for different physical ways to reconstruct the climate, which you can do from different sources. You go for the ice and for all kinds of ways how you try to find out what was the climate 200, 400, 600 years before. But basically we just have one curve. And now we have to figure out, did something happen? Now some problems, of course, is we can forget the idea of a stationary process. Of course, now we can assume, maybe do we have a stationary process? And what's the chance that a random walk from this stationary process would look like this? So that at the last decades there is this increasing thing. But maybe the other hypothesis, it's not a stationary process. Maybe it was stationary over some centuries, but now something happened. The laws of our random walk are now different because of our climate gases, and maybe now we have here in the last decades a very different tendency of our random walk. So it would be a non-stationary random walk, which would of course be a bit more tricky. And so why is this called hockey stick graph? Because this whole thing looks like a hockey stick. I mean, you know, like how a hockey stick looks like this. So you have this hockey thing, and then here you have and this trajectory looks a little bit like this, and we want to know, is this here a new process or is this just by chance? And so this was the whole debate. And so Mann published this paper, and then he got all this problems. So this gave the whole controversy. I mean, it was a real shitstorm, if I'm allowed to say such words in a lecture here. Sometimes this was then called climate wars or climate gate. And this took all nasty aspects that these kind of debates can get when they go into the public, into the press. And so the emails of the scientists were hacked and were published, and people wrote they're insane, and they were it was just a nightmare. And but the only thing actually what these guys were doing, they were saying, let's take such a time series and analyze it to the best of our knowledge. And they said, I mean, there is a tendency that we are increasing in temperature. Of course, the question scientifically gets more and more clear, because, like, I mean, this was around 2000, but if you go now 10 years and 10 years more and more, so we see really, in fact, that this increasing tendency is there. So the more we go in the future, I mean, this cannot be any more neglected. I mean, but that's also clear. But this was done in 1998, where we had 20 years less of data, and the question was a lot more complicated. Already at this time, I think everybody who looked at the data, it was kind of clear that it's increasing. But yeah, okay, I don't want to say too much about this. There's wonderful books about all this climate wars, the dirty tricks that were done by certain politicians and fractions in order to kind of prove that these guys were wrong. But for the purposes of this lecture, I just wanted to show you so that the analysis of a random walk and to figure out, is it stationary or not, does it have a bias or not, is not academic. That can be really the crucial point. And sometimes you just have this single realization, and in your analysis you can do nothing else but try to figure out what's going on here. But that's all I want to say about this climate stuff here. And now in our lecture, so we have seen some techniques how we can analyze random walks, and now I want to analyze analytically compute some properties of simple random walks. For the moment, thank you.